Hi, my name is Rishit Sarkar, and this is my Physics 2212 Lab 3. So the purpose of this lab was to use bar magnets to help visualize magnetic fields and to explore the relationship between the magnetic fields and distances, whether that be on or off axis. So the fundamental physical principles we're using is distance dependence, where b bar is equal to constant times r to the power n, linearization of the equations by simply taking that following equation and multiplying and taking the log of it, and then the Biot-Savart law, which relates dipole moment, magnetic field, and distance. So the main result of this lab was the value for n was found to be negative 2.18. The value for magnetic moment was found to be 13.81 amps times meters squared, and the computational value for B off axis was 1.22 e negative 4 Tesla. So the models that we're using is the bar magnet was modeled as a perfect magnetic dipole, and some assumptions that we're making is that we're assuming the magnitude of the magnetic field was held proportional through some distance, and that n is constant and does not change through the experiment. So the system is the bar magnet, and the surroundings is everything else, including the phone, meter stick, and Earth. So the initial conditions are the magnetic field of the Earth and the magnetometer app on the phone. So the details of this experiment is that the location for the magnetometer was found on the phone, and then that phone was rotated on the axis, and the magnetic fields were found at various distances to get the on-axis magnetic field. These values were recorded in the data table. The phone was then rotated again to find the off-axis magnetic fields, and these values were recorded in the data table. So some observations made was that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. These were the only two observations that we were able to find. So here's the experimental data for this lab. As you see, we recorded the on-axis data to get the linearization equation, and then we recorded the off-axis field. So some experimental calculations, and so taking that previous linear line we had, y is equal to negative 12.799 minus 2.18x, we can take that value to find our value for n and k, and then using the equations we found previously, b bar is equal to k times rn, and the b bar is equal to u naught over 4 pi 2 magnetic moment over r cubed, which is the parallel axis for magnetic dipole. We can set that equal to each other to solve for mu, or magnetic moment, to be 13.82 amps meters squared. So here's our code for this equation, for this experiment to model the off axis. So as you see here, we first created the magnet at the origin, and then we put in their magnitude for the magnetic moment, because that's remaining the same, being 13.81, and I created the function to calculate for the dipole moment by simply taking the R mag and dividing that to get your R hat, and then using the Biot-Savart law to get our B, to calculate for B. And then I simply decided our scale, and then took the distance by taking the distance from the data table, and then I made our observation vectors. And then from there on, I made vectors to help represent the on-axis and off-axis or perpendicular axis magnetic fields for this magnet. And then finally, I'm simply just calculating and then printing out what the off-axis, or be at 45 degrees, and the magnitude of that. And so as you see here, once we run the code, we find that the magnitude of B at 45 degrees is 1.22 e negative 4. And so some similarities that the magnetic fields are pointing in the same direction as in the model compared to the real life, what we found. But some differences is that the expected net magnitude for the magnetic field from the data table was to be 8.42 e negative 5, and the calculated magnitude is 1.23 e negative 4, so the error is about 31.17%. So some sources of error is that there are many electronic devices located in the room, with each providing its own magnetic field, which resulted in the magnetometer misreading the magnetic field slightly. Since so many technologies were in the room, each providing its own magnetic field, the magnetometer wasn't able to get a proper reading. So another source of error was that the human error in data collection may result in the found distances and magnetic fields to be off slightly. So what if you hadn't oriented your experiment to compensate for magnetic north? All the readings on the magnetometer would be off, because the reading would be compensated for true north. This would result in the found magnetic field and magnetic moment to be off from their actual values. So what if we were to stick two magnets together end to end and run the experiment together? So the measurements would show no difference in sign because the direction of the magnetic field would remain the same. However, the magnitude of the field would also double because the magnitude of the field would double, which would result in the measurements would also double. So some final thoughts is this lab showed how a bar magnet can be used to provide for an accurate model for a magnetic dipole. Magnetic fields often on axis are different due to how the magnetic fields loop around, and that the distance a magnet is from an observation point determines the strength of that magnetic field. Thank you.